Okay, thanks, Benny. Welcome back, everyone. So this is the third lecture on delegation of quantum computation, and we're going to talk about a third model, which is a model where there's a classical polynomial time verifier interacting with a bounded quantum polynomial time prover, and we want to do delegation in that model. So there's going to be a computational assumption, whereas everything we did until now was information theoretic. So the starting point is this starting point that I mentioned in the previous lecture. So let me go over it again and first describe a protocol due to Morimae and Fitzsimmons that's in this Posthoc model that involves a quantum verifier, and then we'll make the verifier classical after that. So the theorem kind of justifies this model of Hamiltonian-based computation. So it says that given an input of the form that the verifier is interested in evaluating, so there's a n-qubit quantum circuit and input for that circuit, classical description of them, then there's a way to efficiently, in classical polynomial time, compute some weights, alpha p. There's such a weight for each m-qubit Pauli. So each of the terms are either the identity matrix, the X matrix, or the Z matrix. We can think of the absolute values of these weights as a distribution. And then there's what's called a Hamiltonian. So this is a big exponential size matrix, 2 to the m by 2 to the m. It's just expressed as a linear combination of these Pauli matrices. And the question is, what is the smallest eigenvalue of this Hamiltonian? We're given the promise that if the circuit accepts its input x with probability sufficiently close to 1, then this Hamiltonian has a small eigenvalue. So it has an eigenstate with associated small eigenvalue. And the circuit doesn't accept the input x, then all eigenvalues of the Hamiltonian are large. So here's a very simple verification protocol that uses this theorem, and that's the idea of Morimae and Fitzsimmons. So we have verifier. The verifier is going to have a single qubit quantum computer and the prover. The verifier gets as input a description of the circuit and the input that it wants to evaluate it on. It computes this Hamiltonian HC and sends a description of it to the prover, or maybe it just sends directly the circuit and the input, and the prover will compute the Hamiltonian. The honest prover is supposed to compute the quantum state, psi, such that this state is an eigenstate with the smallest eigenvalue of the Hamiltonian that it's provided as input. Then the verifier is going to select one of these terms p with probability proportional to the distribution induced by the alpha p's. And it's going to request that the prover send it to him all the qubits of the state. So there's not really any message going from the verifier to the prover. There's only this prover sending the qubits of psi one by one. So one by one. What the verifier does is, given the term that it selected, it measures each of the qubits in the basis that's indicated by p. Indicated by the Pauli p. And this gives it some outcomes. Let's call the outcomes bi for I going from 1 to m. And then it's going to accept if the sign of the product of the BIs is different from the sign of alpha p. Okay? And the calculation, which I did already in the previous lecture, that underlies the soundness of this protocol is that this expectation value, you can write it as sum over p of psi alpha p, p psi, and whatever is the state that the prover sends to the verifier, so these qubits one by one, the sign of the product of the BIs is exactly the sign of this term here. And so if the sign is the opposite of the sign of alpha p, then you get a negative contribution to the alpha p's are missing, to this linear combination, and that's what you want to check, because you're trying to check that psi is an eigenvector or just a vector that has an overlap that's as small as possible. So it's sufficient to check that it's negative. Okay, so this protocol works. It has completeness I'd have to calculate what the completeness is. It's going to be something that's related to this, this minus 2/3, where it has completeness somewhat close to 1, and it has soundness somewhat, some constant bounded away from 1. And the soundness is here very easy to argue because the verifier receives the qubits of the quantum state one by one. And so I can immediately say in my proof, let psi be the state that the prover sent to the verifier. Let's analyze this value for that psi, which is just exactly what the verifier measures. And so let's conclude that this Hamiltonian has an eigenstate with small eigenvalue, and so the computation accepts if the prover is accepted. So that's easy. And so our goal is to do the same, but we want to make the verifier classical. And the challenge, as I mentioned in the previous lecture, is going to be if the verifier is completely classical, it doesn't get to see any of the qubits. How do we make sure that these qubits exist? And so in the previous lecture, the way we went around this was by introducing a second prover. And in a certain way, this was the Grillo protocol, delegating the verification that's done by the verifier to the second prover. And the way we ensured that the second prover did the right thing is by using entanglement tests, such as the magic square game. Okay. So now we're going to try to do the same thing, except we are not able to use entanglement. And so we have to introduce another means of gaining leverage over what the prover is. And this means is going to be an appropriate computational assumption. So let me introduce the computational assumption that the results in this lecture are based on. So it's going to be a stronger assumption than what I wrote on the slide. What's on the slide is a pretty generic assumption in cryptography. It's the assumption that there exists a trapdoor claw-free function family. So let me walk you through the slide. So the definition is that we say that a family of functions, so these functions are indexed by public keys, pk, and they map m bits to m bits. Lambda here is a security parameter that you get to choose. And so there's a list of requirements. Most of them are pretty straightforward requirements. So the first one is that there's some key generation procedure. Okay, and this key generation procedure generates keys together with trapdoors. The second requirement is that given the public key, the function can be efficiently evaluated using a classical algorithm. Everything on this slide is completely classical. The third requirement is that each of these functions should be 2 to 1. And moreover, I'm going to make like more of a technical assumption, which is that the two preimages of any image can be consistently labeled as the 0 preimage and the 1 preimage. So I'm going to assume that these preimages always take the form 0, x0 and 1, x1. Okay, this will enable me to refer later on to the 0 preimage and the 1 preimage of the function. Okay, finally, so almost finally, the important property, the claw-freeness, is that any polynomial time adversary or quantum polynomial time adversary, in case we want quantum resistance, is unable to return to me a pair of preimages to the same image. Okay, so the security experiment here is that the adversary is given the security parameter and the public key to evaluate the function. They have to return a pair of preimages, and I apologize, there's a typo, so this should be 0, x0 and 1, x1. Right? This is how my images are labeled. And the adversary succeeds in the experiment if the two preimages are different and they map to the same image. Okay. So that's the claw-freeness. It's called claw-free because you think of these preimages 0, x0 and 1, x1, and then the function maps. You want the function to map both of them to y, and this kind of looks like a claw. Okay, so. And then the last property is the trapdoor. So if you're given access to the public key for evaluating the function, as well as the trapdoor, given any point, it's important that this is any, it's not an average case property, it's worst case. Given any point in the range of the function, it's possible to efficiently recover both preimages. So there's many possible constructions of claw-free function families. For example, there's a very simple construction based on the hardness of quadratic residues, but that wouldn't be a post-quantum assumption. It's also possible to construct them using the learning with errors problem. And in the talk, I'm going to rely on the specific construction of such a family from the learning of errors problem that has additional properties that I'll mention a little bit later. Okay, so for now, let's just fix the family of claw-free functions. And the important properties is that they're 2 to 1. It's hard to find a pair of matching preimages, and the function can be inverted given the appropriate trapdoor. Okay. So this is a completely classical family of functions, but now let's see something fun that we can do using a quantum computer if we have a family of functions like this. Okay, so I'll call this committing to a qubit, but let's just fix a single function from the family, and let's have a qubit that we're interested in. And let's perform the following operations. So the first thing that I'll do is I take my qubit and I append to it m-1 zeros. And I use these m-1 zeros to create a uniform superposition. So this would be 1 over 2 to the m-1 phi, and then here I just wrote sum over all x in 0, 1, m-1 x. So this is pretty easy. I can do this using a bunch of Hadamards. I can rewrite this whole state as 1 over 2 to the m-1 sum over b in 0, 1, and also x of beta sub b, and then b x. Okay, this b comma x, this is shorthand for b, which is a single qubit. It's the qubit that's the qubit of phi, and x, which is m-1 qubits. Okay, I just bundled both of them together. So I just created a uniform superposition. Now my qubit register is exactly the size required to apply the function f. So let's evaluate this function f in an ancillar register. So I'll write evaluate f. We evaluate the function in superposition. Because it's a classical function, I can imagine that I have a classical circuit for it, and this classical circuit I can just implement using my quantum computer. I have to make it. Okay, so this will give me sum over bx. And then I just evaluate it here, f of bx. And now I measure the last register. So this will become y. And when I measure, I get a y that has a certain distribution, but conditioned on a certain outcome y, the first two registers are projected to a state that's consistent with that outcome. So the only pre-images I'm going to be left with are the two pre-images of that y. So the state will be collapsed to beta 0, 0, x0 plus beta 1, 1, x1. Okay, so let me highlight that part here. Okay, so the interesting thing that happened here is that anyone can do this, given any qubit that they want, and the public description of the function, they can implement these easy steps on the quantum computer. And the effect of this transformation is that it has returned a certain string y, and it has returned here what you have is, this is what you could call a committed qubit. So it's kind of it's almost the same as the qubit that you started with, but there's been a relabeling, right? So 0 has been relabeled as 0, x0, and 1 has been relabeled as 1, x1. This relabeling intuitively has the effect of making whatever machine implements this transformation lose control over the qubit. What I mean is that if you're given phi, you can do any kind of operation on it. I can flip it, I can apply unitary, x, z, anything I want. If I'm given only this qubit here, it's much harder. The reason it's much harder is that I don't know what the basis of the space is. Right? The basis of my space here is indexed by these two vectors, 0, x0 and 1, x1. And by the cloud-free property, it's hard to determine what x0 and x1 are given y. So the quantum machine has created that qubit, but it no longer knows the basis of the space in which the qubit lies, and it becomes hard for it to manipulate the qubit. So this is why we call this procedure committing to a qubit. But of course, everything I'm describing is like, honest procedure. I'm just imagining that I do exactly these steps. So we'll see later how it's used. For now, let me observe that even though intuitively it becomes really hard to manipulate the qubit once we've done that transformation, we can still make measurements on it that return to us outcomes that are distributed as if we were measuring the original qubit. And we can do this for the computational basis or the Hadamard basis. So let me spell this out. So measurements. So first, suppose we measure the first qubit using in the standard basis, so sigma z, and we get a certain bit b. Then I claim that the expectation, for consistency with later, I'll label b 0 or 1. So I got to just measure the qubit and got 0 or 1. The claim is that the expectation of the plus minus 1 value of that bit is equal to exactly if I had made the measurement on the original state, okay? This is pretty clear. You can stare at the state, and the probability that I get 0 is beta 0 squared, and it's the same as for phi, and the probability that I get 1 is beta 1 squared. It's the same as for the other one. The fact that there's x0 or x1 written next to it, this makes no difference at all to the statistics of measurements in the standard basis. Okay, so now let's measure in the Hadamard basis. So suppose we measure and let's do this in 2 steps. So let's measure the last m-1 qubits in the Hadamard basis. My claim is that in that case, I'm skipping the calculation here, but you're going to get a string of outcomes, d in 0, 1, -1. And this string is going to be uniformly distributed. And the first qubit is going to be projected, if you do the calculation, in the state beta 0, 0 plus, but you're going to pick up a phase here, d dot x0 plus x1, beta 1, 1. In fact, if you do the calculation, what happens is that you have a phase -1 d dot x0 in front of 0 and -1 d dot x1 in front of 1, but then up to a global phase, I just put the 2 phases in front of the 1. Okay? And now let's measure that qubit in the Hadamard basis. In the X basis. And let's get a bit U in 0, 1. I'm sorry, I'm pushing myself in corners here, but let's get a bit more space. Okay. So then the claim is that the expectation of this bit U that I obtained, corrected for the phase that got introduced, this is equal to, again, a Hadamard measurement. Oh, I'm sorry, I used notation that I didn't introduce these sigmas. Forget about it. It doesn't matter. So it's Z, we're not using sigmas. Z, X, and phi. Okay. The way that I see this is just that my qubit here is exactly the same as the original one, except for the phase. And the phase is like applying a Z operator. And this Z operator is going to, the phase is going to show up when I measure in the Hadamard basis. And so this is why I corrected for the phase here. Okay. So I skipped a few steps in this calculation, but the important points are what I'm going to circle in green. That even though this committed qubit is hard to manipulate, if I measure it in the computational basis, the bit that I obtained is distributed exactly the same as the measurement of the original qubit in the computational basis. And if I measure it in the Hadamard basis, then I get something that's almost exactly, that is exactly distributed as a Hadamard basis measurement of the original qubit, provided that I do this correction. Maybe something that's worth observing is that the correction here is not a computationally efficient correction. So if someone knows the trapdoor, then they can figure out what x0 and x1 are from y, and they can compute the correction. If you don't have the trapdoor, then you can't compute that correction. Okay. No questions on this? I'll continue. So for now, this is just a gadget computation that I performed using the family of functions. Now, let me tell you how to use this in order to get a verification protocol. So this is the protocol that was introduced by Mahadev a couple of years ago. And I'm going to describe to you a version of the protocol that applies to the verification of a single qubit computation. Okay, so a single qubit Hamiltonian, because this captures the main ideas. And then I'll say at the end of the lecture how to go from one qubit to multiple qubits. So for now, let's imagine that we're studying a toy problem. The toy problem is that the verifier and the prover are both given as input a single qubit Hamiltonian. So this is just a 2x2 matrix that I decomposed as a linear combination of x and z. So I'm even making the simplifying assumption that there's no identity or y terms. So it's really a simple matrix. The goal of the protocol is to use the prover to demonstrate or to verify that this Hamiltonian has an eigenvalue that's sufficiently small. Okay. Of course, we could do it by hand. We could just diagonalize, but later this will be extended to many qubits. So let me explain how we're going to do it. So the protocol is parameterized by a family of trapdoor claw-free functions of the kind that I described it before. The verifier can choose a security parameter. There's other parameters of the protocol that I'm not making explicit. And here's how it's going to work. So let me draw the verifier and the prover on the right-hand side. So at the first step, the verifier generates a pair of a public key and a trapdoor from the family of functions, and it sends the public key to the prover. What the prover is supposed to do is supposed to create a state phi, which ideally would be an eigenstate of the Hamiltonian with a small eigenvalue. In general, it can create any single qubit state phi, and it's supposed to commit to it using the procedure that I described in the previous slide, commit. And so remember that this commitment procedure returns two things. First, it returns an image y of the function that the prover will send back to the verifier. And the second thing is that it's transformed the state of the prover to a state that now looks like, sorry, these were betas, beta 0, 0, x0 plus beta 1, 1, x1. Okay, so that's what the honest prover is supposed to do. It kind of encode their qubit into this larger space and give the verifier the information to identify that space through the image y. The verifier using the trapdoor can compute x0 and x1, and so it kind of knows everything that's going on. Okay, so that's the first phase, the first two steps. The second phase, we're going to challenge the prover, and this challenge is going to indicate whether we are trying to recover a computational basis or a Hadamard basis measurement on the prover's committed state. So if c equals 0, this means that we're asking for a computational basis measurement. In that case, the honest prover is going to measure in the computational basis and return to us the outcome b xb that it obtains. Okay. The verifier is going to check that this is a valid preimage of the y that it got in the first phase, and then it's going to record some information. So it's going to write this bit b in ±1 notation and update a counter as a function of the value that it obtained and also the weight that the Hamiltonian associated to measurements in the computational basis. The second case is the case that c equals 1. In that case, the honest prover is going to measure in the Hadamard basis. It's going to get outcomes u and d. U is a single bit, d is m-1 bits. Here, the verifier doesn't do any check at all. She just uses the trapdoor to compute x0 and x1 and updates a value like this and its counter like that. Okay, so we repeat this many times just to collect statistics, and at the end, we return the average of the numbers, and then there's the prefactor is just to correct so that the expectations work out. Okay, so that's the protocol. Let's first check completeness, and then there'll be a lot of work involved in showing soundness. So, but completeness is good to verify as a sanity check. Completeness. So the claim is that whatever single qubit state phi this honest prover there selects, the expectation of this bit O returned by the verifier is going to be exactly equal to the expectation value of that state with respect to the Hamiltonian. Okay. In particular, if this Hamiltonian has a small eigenvalue eigenstate and the prover prepares that eigenstate, then at the end of the protocol, O is going to be a pretty negative value. And in that case, the verifier is going to accept. If H has no small eigenvalue eigenstate, then whatever phi is, the overlap there is going to be large, and the expectation of O is going to be a positive number, and in that case, the verifier is going to reject, right? So I'm not doing all the concentration bounds and all these kinds of things that you do to do a proper analysis of the protocol. Okay, so how do you show that claim? Well, it just follows directly from the computations that we did in the previous slide. By definition, the expectation of O is exactly equal to, so the factor 2 here cancels out with the fact that I do each of the two cases with probability half. And so by definition, it's going to be alpha z times the expectation of AZ plus alpha x times the expectation of AX. We computed in the previous slide these expectations that you obtain from measurements on the committed qubit, and they're exactly equal to alpha z. Okay, so this equal here, this is the part where I'm hiding some of the calculation, but this is what happened in the previous slide. This was the argument that by making measurements on the committed qubits, which are where these A and X's come from, you recover these things that are distributed just as measurements of the original single qubit that you committed to. Okay, so this tells us that in the case that the prover behaves as intended, everything works smoothly. So now, okay, so if there's no question, I'll continue and talk about how we do soundness. Of course, that's the interesting part. It's also the part that's a little bit more technical. So I'll try to say as much as I can without being too technical. But try to show you how we address this. The main question that we need to address in this protocol is for soundness, we're taking a prover that succeeds with in the protocol, let's say with high probability. So it's a prover that manages somehow to make the verifier set this O in the end to be a pretty negative value by reporting the right outcomes. And I want to claim that the only way to do that is for the Hamiltonian to have a small eigenvalue eigenstate. So I need to say, where does that state come from? But my interaction with the prover only involves classical information. So how do I, from this classical information, claim the existence of a quantum state? In the case of a single qubit Hamiltonian, it might seem like there's workarounds, but you have to keep in mind that our goal is to run this protocol where the verification is to quantum states that don't have any efficient classical representation. So it's not like I'm going to be able to construct a classical representation of the state just from the data that's collected in the protocol. I have to show that it exists, but I want this argument is not going to construct it just from the classical data alone. Okay, so in order to do this, I'm going to model the prover in a certain way. So let's take an arbitrary prover. And there's two phases in the protocol. The first phase I'm kind of going to put aside and focus on the second phase. So in the first phase, this is what's called the commitment phase. The prover returns Y. Okay, I see this, I get this as a verifier, and its state is psi Y, which is a state I have no control over. It's just like some state that's the prover. If the prover doesn't have a pure state, let's just give it a purification of the state. Okay, so this is the prover and the environment, everyone. I just described their state using psi Y. Okay, in the second phase, there's two challenges. Either I ask them to measure in the standard basis, or I ask them to measure in the Hadamard basis. In both cases, they return to me an m-bit string. And in general, this m-bit string is the result of an arbitrary measurement for both bases. However, what's an arbitrary measurement? An arbitrary measurement is you take your qubits, so that's the state psi Y. Maybe you add some ancillas, but let's just put the ancillas in psi Y already. Then you apply a unitary transformation. And then you measure a subset of the qubits. You measure exactly as many qubits as you have to report bits. That's the most general thing that the prover can do. Technically, I'm maybe using Naimark's dilation theorem, but it's this is just whatever circuit they're applying. In particular, because there's only two challenges, computational or Hadamard, whatever unitary transformation that the prover would do when I ask it for a computational basis measurement, I can imagine that it's already done in psi Y. In other words, think of this state as the state that the prover prepared, and he's just ready that if I ask them for a measurement in the computational basis, they just right away measure in the computational basis. There's no unitary to apply. If they wanted to apply unitary, they can have done it, but they did it before. Okay. Of course, in the Hadamard basis, they could do something else. They're going to make some other unitary that's going to shift the basis. So this means that my arbitrary prover, in case the challenge C is equal to 0, they're going to measure all qubits, oh, sorry, not all, the first m qubits in the computational basis. So this is an assumption. It's an assumption without loss of generality, just by shifting the way I describe the prover. And then on challenge C equals 1, then in that case, I mean, I can't control both challenges, so they'll apply some arbitrary U on their whole space, and then plus after that, they'll measure again the first m qubits in the Hadamard basis. So it might, don't be confused that I'm not making an assumption that they actually measure in the Hadamard basis. They make any measurement they want. Any measurement is unitary plus standard basis. And if I want to say any measurement is unitary plus Hadamard basis, I just have to conjugate the first unitary I talked about by Hadamard, right? So it's not an assumption, it's just a way to model what they're doing. Okay, but I'm just starting to get my hands on the prover. In particular, I'm starting to get my hands on some qubits because there's these m qubits there that I'm saying these are the qubits that are being measured. If you're returning a string, you have to be measured. You have to obtain that string by measuring some qubits. Okay, let me introduce a little bit of notation that's going to be useful for later. So this is notation. Let me introduce it and I'll explain it. So I'm going to introduce two observables. The first one, I'll call it z hat, because this is what the prover does in the case I ask it for a computational basis measurement. And remember that in the case of a computational basis, they gave me back b and x, but I only used b as an estimate. X I used to check that it's a pre-image. So this is just going to be z on the first qubit, and then identity on the m-1 remaining qubits, first qubits, and then identity on everything else. Okay, so this is an observable. And it captures the distribution of the bit b that the prover records. So the expectation of -1b in the protocol is exactly equal to psi y z hat psi y, okay? By definition, because by definition, to get b, the prover measures the first qubit. And this is what this z hat captures. In a Hadamard basis, it's a little bit more complicated, but I can still write it out. So using the way I modeled what happens in case of the challenge 1, I first have this unitary u, and then after that, I do a measurement in the Hadamard basis. So this measurement in the Hadamard basis, its outcome I can represent in the following way. So I can write, there's an m qubit Hadamard here. And then after the m qubit Hadamard, I measure a u and a d. This is 1 bit and this is m-1 bits. I do it in the Hadamard basis. So this is why I'm conjugating by Hadamards on the outside. Okay. And then u dagger. So these are definitions. Okay. I'm defining these two. Oh, sorry. I forgot that I'm summing over u and d. And I'm going to put a phase here, which is the phase that the verifier computes. So this is done so that I can write an analogous equation, which is expectation of, well, let's just, okay. Okay, so I just defined this observable x hat, and it just follows directly from the way that I modeled the prover. I said on challenge c equals 1, this prover applies a unitary and measures in the Hadamard basis. So I said, okay, well, how does that look like? I apply unitary, I change of basis to the Hadamard basis, and I measure, and I get these strings. And then in the protocol, these are the strings that the verifier gets. What does it do with them? If you remember the protocol, if you want, you can open my slides. I put them on the Slack. So if you remember the protocol, it computes a value AX, which is just that here. And so this is what I did here. I put it in the phase. And so the claim is that the expectation of this value AX that's stored by the verifier in the protocol is exactly equal to the expectation value of the observable X hat on the state psi Y that the prover has at the end of the first phase of the protocol. Okay. So at this point, I didn't do anything, but I did very important modeling choices. I gave name to things, the state of the prover, the actions that it can perform. And I introduced observables on the prover's state that model or that capture the expectation value of the outcomes in the way that they are recorded by the verifier. Okay. Continue. So what I'd like to claim, the goal in the protocol is to claim that the outcomes that are recorded by the verifier, these outcomes could have been obtained by regular computational and Hadamard measurements on a single qubit state. If that's the case, then that single qubit state, this is what I say is the state that witnesses that this Hadamard has a small eigenvalue. And what we did as a first step towards that, except that this state psi y here, this is not a single qubit state. It's an arbitrary many qubit state. So it depends on the prover. So there's a couple more steps that we need to do to get a single qubit state. The main step is the following. That step is going to extract the single qubit from the many qubit state of the prover using an idea that comes from it's a kind of the idea of teleportation. So here's a lemma that you can do by direct calculation. So let's take two arbitrary observables, okay? For example, the two that I described on the previous slides, but doesn't need to be, they could be equal. They could be just one-dimensional things. They could be really anything. And let's take a state in that Hilbert space. And now let's define a map. And this map is going to create a qubit from these two observables. And the way it does it is that it starts from the Hilbert space and the state psi. And the first thing that it does is that it appends an EPR pair to psi. And then it does what intuitively you can think of as a teleportation measurement between psi and the first qubit of the EPR pair. The way it does this teleportation measurement is that as for teleportation, it uses single qubit Pauli operators on the first qubit of the EPR pair. But in the state psi, we don't really know what it is. The only access we have to it is through these two observables that I defined earlier. And so these are the matching observables that are introduced here. Okay, so I can define psi like this. And maybe the claim that I make about it is the following. So maybe there's two parts. Like a first part, just for intuition, is that if H is the space of a single qubit, and these observables are just the regular Pauli observables, then what I did is I really did teleportation. So then for any psi, V psi is equal to, it exchanges things. So it moves the EPR pair to the first two registers, and psi lands in the third register. So the one that's called B up there. And this is on H and A, okay? That's a direct calculation. You can do it. The second part of the claim, maybe I should have said that V is an isometry. It's also something that you can check. There's no property that's required on Z hat and X hat other than the fact that they're observables, so they square to identity. But you can verify that V preserves lengths. And the second, and that's the important part of the calculation, I'm going to skip the calculation, but I'm going to tell you what happens. If you apply V to some state psi, and then you measure the last qubit, so I have identity, tensor, in the computational basis, then the expectation value is the same as if I had measured my original state psi in the basis Z. I can do the same in the Hadamard basis. And what I'll get is not quite this, but there's a correction term. Which is like that, okay? So you can observe that everything that I did checks because if Z said checks because if Z hat and X hat anti-commute, then, oh, there's a factor half. If they anti-commute, then these two terms here are equal and the half will cancel each other, itself, and I'll just get X hat, okay? The content of this lemma is that this is what allows us to define a single qubit from this prover. So it's kind of the key step in the proof. That step says that I can take any prover in the protocol, run it for the first phase, and obtain a commitment string Y from that prover. The way we modeled the prover before, its state at the end of the first phase is some arbitrary state psi Y, which can be on many qubits. But now I also said there's two different actions that this prover can do on its state corresponding to the two different challenges. And these actions are encapsulated into two observables, X hat and Z hat, two different measurements that I have no control over except that they're just valid measurements. Using them, I defined an isometry which comes from this intuition of teleportation, and I can apply this isometry V to the state psi y. Now this will give me a state in that space H tensor C2, and I trace out the two first factors. There's no prime here. Okay, I trace out H and A. So this is a state, single qubit state, density matrix on C2, and for any prover, I can define it. And I note that so far I'm really just manipulating symbols. I didn't assume anything about the prover, not that it succeeds in the protocol, not that it's computationally bounded, nothing. But what I did is I did manage to say that from the actions of the prover in the protocol, I can define a valid single qubit quantum state. Okay, that's the conceptually difficult part of the proof, I think. Now the kind of technically involved part of the proof is say that measurements of this single qubit in the computational and Hadamard basis, whether these are related to the outcomes that are registered by the or recorded by the verifier in the protocol. So this is what the next lemma does. Okay, maybe I need to keep these like this. Okay. So now finally, there are some assumptions. There's two assumptions. One is benign, the other is important. So the benign assumption is that I'm going to assume that the prover succeeds with probability 1 when it's tested. So if you remember for the case of the challenge C equals 0, I test that it always gives me a valid preimage of the string Y that it gave me in the first phase. Let's assume that it succeeds in that test with probability 1. Of course, that's a strong assumption. In the protocol, I can only assume that it succeeds with probability maybe close to 1. Let's imagine that we repeat this many times. I just make it really close to 1. Worry about this later. And let ρ be defined from the prover as it's defined here. So that's the same one. Then the claims are as follows. If this hypothetical state ρ is measured in the computational basis, then the bit B that I obtained by measuring it is distributed exactly as the bit B that's recorded by the verifier in case of the challenge C equals 0. But that part of the claim is easy to verify. In fact, it directly follows from this equation, because on the left-hand side, I have a measurement in the computational basis of my extracted qubit, right? I applied V to psi, and I'm looking only at the last qubit. And on the right-hand side, I have by definition the bit distribution of the bit B as it's recorded in the protocol. This is the way I had defined Z hat is for this to check. So this is actually very easy. Oops, sorry, easy to verify from the definitions. The second part is the hard part. The second part is I want to say the same thing in the Hadamard basis. So I can look at the same equation that I had for the Hadamard basis. This is the expectation of a Hadamard basis measurement of the committed of the extracted qubit, and I'd like it to be equal to just this. Okay, because this is what the verifier records in the protocol in the case of C equals 1, but there's a correction term. There's this here. And of course, intuitively, there should be, because so far there's really, I didn't make any assumption that the prover is computationally bounded. So they can, invert my function and give me any kind of outcomes that they want to convince me that, this Hamiltonian has an eigenvalue -1, even if it doesn't, right? You can do that. So I need a computational assumption. And the computational assumption at some level is going to be that, well, I want this to be distributed the same as just that. Okay, if I wrote it in this way, then it wouldn't be very satisfactory. So we're going to make a computational assumption about the family of cloud-free functions, and that computational assumption is going to imply what I just wrote here, in the sense that any distinguisher for these two expressions, I am going to be able to transform in an efficient attacker for the computational assumption by using the distinguisher and also using the prover. So as long as the prover is computationally efficient, then I'd have broken the assumption. And that part I'm really not going to be able to explain, but I do want to state what the assumption is. It's kind of a nice but non-standard assumption that we have to throw in onto our definition of the trapdoor cloud-free function family. So I have the trapdoor cloud-free function family as I described it before, and the additional assumption is that for any quantum polynomial time adversary, and here I really need the assumption to be post-quantum, because for soundness of my protocol, of course I'm talking about a quantum prover. So it should be the case that no quantum polynomial time adversary can succeed in the following security game. So in the security game, the adversary is given as input the security parameter and the public key for the function. And it has to return two things. It has to return to us a preimage X and a equation D. And what should be the case is that if I look at the other preimage, so I evaluate the function to get y, and then I look at the two preimages, x0 and x1, so one of them is x and the other is something else, then this string D that was returned to me, first of all, is non-zero, and second is an equation in the parity of the two preimages. So there's a parity symbol there missing. Okay. So the adversary is required to provide one preimage plus an equation in the two preimages. So this is a stronger requirement than claw-freeness, because if I have an adversary that breaks the claw-free property, it can break this property here simply by recovering two preimages and then giving back to me one of them, and then an equation in their parity. It's easy to find a non-trivial equation in their parity if you have both preimages. So it's a stronger assumption. It's called adaptive hardcore bit because a more standard hardcore bit assumption would be that the adversary is given as input a uniformly random equation. And in that case, it's hard for it to predict the right-hand side for the equation. If d dot x0 plus x1 is 0 or 1. Here I'm giving more power to the adversary. They can choose the equation themselves. And this is why in the assumption, we need to require the equation to be non-zero, because if I allowed the equation to be 0, then that's always a valid equation. And so the adversary could trivially do that. Okay. It's a very strong assumption. The assumption is that the adversary can't find any non-trivial equation in the two preimages as well as a preimage. So it's a non-trivial assumption, but you can construct a scheme, a family of claw-free function families based on the learning error problems that satisfies this assumption. Okay, so I'm not going to show the construction for the lecture, but it's in the references. Okay, and so the part that I am skipping is exactly the link between, this is what this here. So the computationally indistinguishable that holds in the second part, that shows up in the second part of the lemma, relies on this adaptive hardcore bit assumption. So what you can show is that if a quantum polynomial time, there is a quantum polynomial time distinguisher between this and a measurement of O in the Hadamard basis, then this distinguisher together with the prover's actions can be transformed into an adversary that breaks the adaptive hardcore bit assumption. Okay, once we're there though, we're pretty much done in terms of our soundness analysis. So let me try to recap a little bit. So what we showed is that if you take a prover that's a quantum polynomial time prover that's assumed to succeed with probability 1 whenever it's asked for a preimage, then this prover is going to lead to an outcome O recorded by the verifier, as I described on the first slide. So this outcome O was obtained from the prover's answers in the case of the two challenges. And in that case, it's going to be that the expectation value of this outcome is, I wrote computationally indistinguishable because this is what we show, but these are distributions on one bit. So computationally indistinguishable for this case is the same as statistically indistinguishable. From the expectation value, with respect to the Hamiltonian that we care about, of some state phi. This is the state, sorry, I should have written Ho here. It's the state Ho that we defined as the extracted qubit. So from any prover, we can always define a single qubit state. And if the prover is computationally bounded, then this single qubit state is going to have this property, okay? That measuring that single qubit state or whatever the verifier records in the protocol are computationally indistinguishable. Okay, so there's two small issues with this. First is the assumption that the prover succeeds with probability 1 in the preimage test. So this I'm not really arguing about, but you can, for example, repeat the protocol many times to make sure that this probability is close to 1. And then there's a simple reduction that reduces to this case. In fact, I'm sorry, you don't need to repeat the protocol. You can trade off the success probabilities in the two branches C equals 0 and C equals 1 against each other to make sure that the C equals 0 branch has a success probability as close to 1 as you want at the expense of maybe lowering the other success probability a little bit. Okay, what requires a little bit more work now is extending to a real Hamiltonian. That's a Hamiltonian that acts on multi-qubits. There's two different steps that you need to make in order to do that. The first is I need to be able to recover expectation values of multi-qubit terms that are many x's or many z's. So if this is the only thing that I needed to do, then I could still have a protocol with just two challenges. One challenge would be measure everything in the computational basis. The other would be measure anything in the Hadamard basis. And so it turns out that if this is the kind of protocol that you consider, the analysis that I described to you is not too hard to extend. There's just one additional property that you need for the function family, which again can be obtained from learning with errors. I want to describe that property to you because it's a cute property called collapsing property. It's a strengthening of the notion of collision resistance that was introduced by Unruh in the analysis of showing that certain primitive, I think it was a commitment primitive, is post-quantum secure. So the security game for the collapsing property is as follows. So you have the adversary and you have the challenger. So the challenger sends to the adversary the name of a hash function, pk. The adversary is allowed to prepare any state that's a superposition over pre-images to the hash function. Okay, so it's just a state that needs to have the right size with respect to what size of pre-images this hash function takes. And it sends it to the challenger. What the challenger does is that it evaluates the hash function and it measures an image y. So this projects the state into, you can define this for many to one hash functions, but let me do it for the case of 2 to 1 hash functions because that's what's relevant for this talk. So it's going to project it similarly to before to something that looks like 0x0 plus alpha 1 x1. Okay, so you just collapsed two pre-images. And then you're going to return to the adversary one of two things, and the adversary is going to have to distinguish between the two of them. So either you return to it, so let's call this psi y, since this is how it was called before. Either you return to it psi y, okay, or you return to it measured psi y. So you measure, which means that you return to it like a decoherent version of it, which is just going to be alpha 0 squared x0 x0 plus alpha 1 squared x1 x1. So this is like saying, instead of keeping the two pre-images in a coherent superposition, I return this superposition measured. And the collapsing property states that the adversary should not be able to distinguish between these two cases. It's the strengthening of collision resistance because if I can find two pre-images over certain y, then I can create the state x0 plus x1, send it to the challenger. It's going to either measure or not. And then when I return it back, I can create another copy of that state and check if they're the same by this thing called the swap test. So if the hash function family is collapsing, then it's also collision resistant. But in the other way around, I think it doesn't hold. So there's some contrary examples where it doesn't hold. Okay, so this was just to say that that's an additional property. I'm not telling you how it's used, but if you have that additional property, this allows you to do the multi-qubit analysis for the case where you have only terms of the form x and z. If you're trying to handle a general Hamiltonian, then you'll also have terms of the form like x, z, x, x, z, something like this. And there's one more property of the family of functions that you need in that case, but it's starting to be a lot of properties, so I'll skip of the technical definition of that property. Again, you can construct it based on learning of errors. And so the result of all this is that you have a form message protocol. You can ensure that this completeness of the protocol is negligibly close to 1. The reason it's not exactly 1 is because you need to require the prover to not return to you an equation D that's equal to 0, because that would be cheating. However, the honest prover does get 0 as its equation with probability 2 to the minus number of qubits. And so that's just something that's unavoidable. So the completeness is not 1, it's negligibly close to 1. And the soundness, if you work everything out, you can get the soundness that's 3/4. Okay, so let me just end with some recent extensions on the Mahadev protocol that I presented and maybe a couple open questions. So there's in fact been many extensions. I guess I won't describe any of them in detail. There's a couple of nice papers that have the same starting point. So these two papers, first of all, have the contribution of giving a fairly high-level, clean formalization of what goes on in the protocol. So removing some of the details and just describing the prover using a pair of measurements. Using that clean formulation, they can prove a parallel repetition theorem for the protocol. And that's something that doesn't exist generically because the protocol is an argument. So we don't have parallel repetition, general parallel repetition theorems for arguments. But using the particular structure of the protocol, they're able to show parallel repetition. And then once they've shown that, they do two different things. The first protocol uses the Fiat-Shamir heuristic to obtain a non-interactive protocol in the random oracle model. And the second one combines the protocol with some classical techniques such as efficient non-interactive zero-knowledge proofs, things like that, to obtain a very efficient protocol in the random oracle model, and also they use a CRS. There's a paper that was mentioned in the chat earlier that considers an extension to sampling problems, and there you're able to verify not just that the circuit returns 0 or 1, but the verifier is able to obtain, in a guaranteed form, samples from a distribution that's computationally indistinguishable from the distribution that you would obtain by making measurements on the qubits of the a small eigenvalue eigenstate of the Hamiltonian. These kinds of extensions is motivated by trying to apply verification protocols to the so-called quantum computational supremacy experiments. Where there the task is for the quantum device to provide samples from a certain distribution. And if the samples satisfy certain tests, then based on some complexity theoretic assumptions, you get the guarantee that the device must have done something that's beyond classical polynomial time. Unfortunately, the verification of these problems is almost as hard as cheating in them. So it's a big problem to get efficient verification. And so that's not solving that problem, but it's a step in that direction. And finally, in work with Tina Zhang, we extended a little bit the protocol to show that it has a property of proof of quantum knowledge. So we extended the soundness analysis to not only show that there exists a quantum state that satisfies, that certifies that the outcome of this circuit is 1, but also that the prover in some sense knows that state. So you can explicitly extract the state from the prover. And this is, I incorporated some of our work in the way I did the presentation earlier. There's also a paper with Giorgio, which achieves something similar. It uses some of these ideas to get a different delegation protocol, again, with a classical verifier and computationally bounded prover. The base ideas are the same, but then the model is different because it's in the measurement-based model instead of the Posthoc model. An advantage of that work is that it's a more atomic protocol, and in particular, it's composable. So you can use it in conjunction with other primitives. Okay, a couple open questions. I think it's an open question whether you can reduce the interaction from 4 to 2 messages without introducing an assumption such as a random oracle or maybe just a CRS. I think an interesting question, I already mentioned the question of whether you can achieve the same without computational assumptions. That's not ruled out at all. Maybe it's possible. Even staying within computational assumptions, it would be nice to have a wider variety of computational assumptions. So far, really, the 2 handles that we can get our quantum provers are the 2 that I presented in the past lecture. And this one, either using entanglement or using computational assumption, but really specifically in the way that I described here, it would be nice to have a little bit more diversity. And finally, there's something, and this is partially addressed by this work here, which is that this protocol is very bulky, like it's very monolithic. It's hard to say, what if I care only about a simple circuit? What is if it's a Clifford circuit? It has just a couple T gates. What if it's simple in some way? It has small depth or maybe a small number of qubits. Do I get a more efficient verification? Can the prover also be implemented in using resources that are commensurate with the computation that I want to perform? And I think because of working in this Hamiltonian model, there's a lot of resources that get lost in transferring from one model to the other. I think it would be nice to have a broader understanding of how the protocol can be specialized to different classes of more specific classes of computation. Sorry, I just realized I'm 1 minute over, so I'll stop here.